Welcome to solverfy.
In this problem, we have light shining through three separate materials, each with a different index of refraction. And we can see on this diagram that there are two possible ways for the light to enter material 3. And in general, because of this extra distance traveled by the second ray, these rays will be phase shifted one from the other. They want us to find which wavelengths of visible light will result in a complete constructive interference between these two rays, which means that the extra distance traveled by this second ray here, labeled R4, will have to be some multiple, some integer multiple of the wavelength of the light. So what we're given are the indices of refraction, which are N1 is equal to 1.68, N2 is equal to 1.59, and N3 is equal to 1.5. We're also told that the thickness of this middle layer, L, is 415 nanometers. So like we said, the extra distance traveled, which is going to be twice L, must be some multiple of the wavelength. So the wavelength is lambda, but it's actually not lambda. If lambda is the wavelength in a vacuum, the wavelength in this material is lambda over the index of refraction, which is N2. And it's got to be some integer multiple of this, so we'll multiply by some integer m. So m is 1, 2, 3, 4, etc. Now we're almost done. We just have to account for any other possible phase shifts that may occur. And when you have light reflecting off a surface, if it goes from a lower index of refraction to a higher index of refraction, the reflected ray will be phase shifted by half a wavelength. So we have to correct for any of these possible phase shifts. So when we go from N2 to N3, we're going from higher to lower, so there's no phase shift here on the reflected ray. On this first surface here, when we're going from N2 to N1, well, N2 is less than N1, so there is an extra phase shift of half a wavelength here. So this equation here is offset by half a wavelength, so we have to correct for that. So we can either add or subtract an extra wavelength, or an extra half wavelength. And I'm going to subtract an extra half wavelength. Now we can solve for lambda. We have that lambda is going to equal 2 times N2 times L divided by m minus 1/2. And for each integer m, there will be a different lambda that satisfies this constructive interference requirement. And so we have to find the wavelengths lambda that fall in the visible spectrum. And I'll just remind you that the visible wavelengths are between 400 and 700 nanometers. So we just have to plug in various values of m, starting at m equals 1, and see what we get. So m equals 1. M equals 1. We have, well, first let's just write here that this numerator, which is going to be the same for everything. So this numerator is 1320 nanometers when you plug in the values that are given. So this is going to be over m minus 1/2. So m equals 1, the corresponding wavelength will be 1320 divided by 1 minus 1/2. So this is 1320 divided by 1/2, which is just double of 1320, which is going to be 2640 nanometers, which is outside the visible spectrum. So this is not a solution. M equals 2. Plug in m equals 2 to here, and the corresponding wavelength works out to 880 nanometers. That is also outside the visible spectrum. So let's try m equals 3. The corresponding wavelength in this case is 528 nanometers, and that is in the visible spectrum between 400 and 700. So that's a solution. And next we'll try m equals 4 to see if that's still in the visible wavelength or if it has left on the other end. So m equals 4. We get that the corresponding wavelength is 377 nanometers, which is less than 400 nanometers. So this is no longer in the visible spectrum. So the only solution is lambda equals 528 nanometers.